Welcome to Smart Materials, because that's what we've ended up on. We're going to talk a little bit about smart materials, or at least I am, because it's kind of offline, so I'll just talk and we'll see where we go. First of all, we have to define what we're looking at. So out of the topics that you were offered, the choice has been smart materials, and so we'll have a look at those and then we'll take it from there. So what is a smart material? Hang on. So in reality, instead of being really smart, it has to have some kind of response to a stimulus of some kind. That is usually something very simple. So what we think of as a smart material normally in the media would be some kind of incorporated sensor that does something, but a much simpler case would be a material that responds to some kind of stimulus in some kind of simple chemical way. A good example, or a good simple example, would be a type of gel that thickens in the presence of calcium ions, for example, behaving very much like blood clotting would. So if we imagine that, we can think of something that will bind to calcium. So we've got some kind of polymer, and it will have to be dissolved in water. Otherwise, it won't be, first of all, it won't be a carrier of ions, and secondly, it won't be very easy to mix. And then we can have groups on the side that attach to calcium. So they would be maybe acid groups, O double bond O minus, and they will attach to calcium ions, for example, Ca2 plus, and they will be attached to, from the other side, OO minus. This would be a simple example of a smart material, which is very dumb. All it does is get thicker when it's exposed to calcium ions, and it gets thinner if the calcium ions are removed again, which may or may not be easy. In the case of blood, what we do to remove them is we add a stronger complexing agent that will pull the calcium out and hide it, and then we will need to add more calcium to cycle it again. The problem being obviously that the original calcium is still there, locked up in the original chelating agent, and so we will have a limited number of cycles, but it does behave very much like blood. If we want to have a more useful mechanism, so from this, hang on, I'm going to draw it, we might have something like this chromophore, where when light comes in, it will absorb it. Maybe if we're lucky, we can get it to fluoresce as well, so to give out a different color of light. Let's have it doing that. I should have had a longer wavelength there. But let's have a longer wavelength coming out so we can see that it is there. Now when it attaches to our calcium ion, so let's move this up to here, Ca2+, the electrons from these rings are pulled into connect with our calcium ion, and we can detect, in effect, by the color of light that comes out or the color of light that is absorbed, we can detect what our species is, or at least to a certain extent. Things like this are used very commonly in biology to detect ions. So there is a calcium ion dye. It's not this, I just drew that randomly, but it looks somewhat similar. Yeah, good. And alternatively, we would have measurement systems for other things. We might attach a particle to it and use an antibody, for example, and the mechanism that we're going to use very often is the same. We want to see it with some light, because it's an easy and simple way to detect things in situ. If we make this molecule a biomolecule, so we attach it to a protein, then it will survive inside the body for a relatively long time, and then we can use it to probe cells, for example. Biology has used a whole load of different purposes to generate smart materials. So the other part of the subject was biomimetic, to keep it inside our degree program, to make it a little bit more applicable. And what we find in biology is a whole range of types of chemistries that are used by things like single cells, including bacteria, but also our single cells, in order to detect things. So if we have a protein, it is really using a more simple end of protein, maybe an acid group, to detect an ion. Bacteria use simple outside groups to detect whether they want to go to food or whether they want to go away from poisons. They are relatively simple organisms. And we can use this principle to make smart materials. What we would like to have is some kind of response to a thing that we are going to apply, and it could be anything at all. So the big alternative would be a redox reaction that is maybe reversible or maybe not reversible. So we're looking at the calcium exchange. That's a reversible reaction. We can also look at an irreversible reaction, or a mostly irreversible reaction, and that would be the polymerization of dopamine, for example. Why dopamine? Dopamine is a major component of the glue that mussels, the freshwater animals, or fresh or saltwater animals use, so shellfish use, to attach to surfaces. So this is dopamine here, the molecule of interest, but we're going to use a simpler one, which is pyrrole, this molecule. It does a very similar thing, which is why we're going to use pyrrole as an example, because there are less atoms and it does a slightly less complicated thing. So what happens is the pyrrole can become oxidized. It becomes oxidized to a radical cation. It gets oxidized to this radical cation. Oxidation is loss of one electron, so we lose an electron out of these orbitals. If we look at pyridine and pyrrole, it has a ring structure with the lone pair of the nitrogen participating in this ring in the pi electrons, so they're in this double bond, and this behaves similarly, because if we think of the orbitals, there are orbitals on all of these atoms, on these carbon atoms, that look the same. We take out one electron from that whole pi ring, and it means it's positively charged somewhere, and it's one of these, and it's also got a single electron which it needs, so it's unhappy. This oxidized pyrrole can react with another pyrrole, a normal one, by taking electrons from it. So let's do that with proper electron arrows. Just in case you don't know, electron arrows are double-headed if they're 2 electrons and single-headed if they're 1 electrons, and they're 1 electron, and we always draw them curly to denote that their electron arrows are not the reaction arrow. So we push the electrons into this bond, that pushes this bond across to here, and that pushes this bond across to here, flip, and that's what it wants, but this is going to make it, this is going to move the positive charge over onto this one, and we are going to generate a new species. Let's resolve that. Let's resolve this here. So we're going to end up with a new bond here. We're going to end up with a bond here and a bond here, and we have an unhappy reaction, and the positive charge ends up over here, and this is now happy again because we've taken an electron, or we've taken 2 electrons back. We've taken a share of 2 electrons, but it will push these. It will push these out of where they were, but let's just draw them back where they are. We have to get rid of this. Oh no, let's do it like that. So let's do it like this. Boom and boom, and get rid of the plus. So now we've got something that looks fairly symmetrical, but it's got to get rid of these 2 hydrogens to be able to close back up and be aromatic again, because this type of structure with 2, 4, 6 electrons in a pi structure is very stable. So to get back to that, we need to get rid of some hydrogens, and we will do that by taking them off. And we might get rid of them as H pluses, or we might get rid of them as some other species, but let's get rid of them as H pluses, so we can have this electron into here. That makes this one happy, and we can have this electron into here, which makes this one flip back to where it should be. And now we get rid of these hydrogens, and we go back to this and this, which is good, but we have a problem with charge because we've got rid of 2 pluses, so we now got a negative charge. The negative charge is over here because this is the one that lost a plus. It's over on this nitrogen. So now we're going to have to do something about that. So we will have to have further reaction. This is similar, but not identical, to the reaction of dopamine, which is the real biological version. In the reaction scheme of Pyrrole, we don't usually end up with a negative charge in between. I've done that for neatness, to get rid of the 2 hydrogens at the same time. Otherwise we end up stuck in an ugly structure in between. This thing can now attack some other Pyrrole, and particularly some oxidized Pyrrole, to get rid of the positive charge. This reaction goes on and on and on, and we end up with links between all of the Pyrrole, so we end up with a polymer. Let's have a look at the dopamine. If we oxidize this, it does a similar reaction, so it loses an electron from its ring. Let's draw that out as 3 bonds, just 2. And the same will happen, that we'll end up with a positive charge on here. So we end up with a dot, 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 plus, dot. But in this case, we're going to take this hydrogen off. So we're going to take this bond and put it into here, and that will give us our plus back. So that can resolve this, and this goes away. So if we resolve that reaction, we end up with an O there, plus H plus. And we can do that twice to form this species, which is the oxidized form of dopamine. The oxidized form is not that reactive, but in its partly oxidized form, let's do 1 like this, in its partly oxidized form, plus dot, it can do all kinds of things. The nitrogen can react with it to form a ring here. I think I've drawn it too long. The nitrogen can react with it to form a ring on this side, a secondary ring, which also resolves the positive charge, but it generates a new chemical species. And this can also polymerize with other dopamine very similar to this. Probably here, thinking about it. We'll have a look at that later. So our dopamine does a similar reaction to the Pyrrole, but the Pyrrole is simpler because it doesn't have these 2 OHs which also react, and it doesn't have this other ring-forming reaction, which makes it super complicated. It has a lot of things it can do. The Pyrrole only polymerizes, and it polymerizes particularly well when about half of it is oxidized, because then half of it is in this, which I've removed, in the positive radical state, and it will react with other things. We can do that with iron, as an iron oxidizing agent. We can also do it with oxygen. It happens on its own, and we can also do it with electrochemistry. Why is it a smart material? If it sees an oxidizing environment, it will change its properties. So this is our polypyrrole. Hello. Yeah, this is our polypyrrole, and it's the analog. Hello, hello. Okay. Let me start again. This is our polypyrrole, and it's an analog of a semiconductor. So if we think of a semiconductor, it has a band gap, and it has filled states down here with electrons in, and it has open states here, and we have to jump electrons up into the band gap to be able to start it. So in its normal state, it's not conducting. This is much the same. It's got electrons in all of its orbitals, and it doesn't have any electrons that can move easily because we'd have to break a bond. But if we do the same thing that we did before, so we remove an electron here by oxidation, so we generate a plus dot radical in here, then this plus dot radical can move around. So if we apply, let's have it on this end, so if we apply a voltage, a positive voltage on this end and a negative voltage on this end, then the hole will tend to move in this direction, so the electrons will move in the other direction. So let's do that. Our electrons move in this direction. That makes this happy again, but so it makes this form this species, and it's happy nominally, but this one is not. So let's do it like that. Let's rip out these and fix it. Bang, bang, bang. That's our new structure, and our positive charge is over here because the electron came from the nitrogen. And now we have to finish this. Boom, boom, boom. Yes, that's correct. Then we have to finish it. Obviously, we will need some way of getting this back to its original state. So we need to get this up to here and this to here, so that we get back to our normal state. That will kick our electron back out again, so we have to work out how to do that. Let's have a quick think. Okay, I worked out what I did wrong. There's supposed to be a single electron here, which is unhappy. So I've sketched on all my lines. These are all single electrons moving, so it's a radical process now. It's not really in 2 steps, but it's easier for me to think of it if I do it in 2 steps. Then we have our formation of this double bond. It needs 2 electrons, one from this, so it's a one-armed arrow, and one from this double bond, one-armed arrow. The other electron left over goes onto the nitrogen to satisfy that dot, the radical, and this one goes over here. It needs another electron from this double bond, and this one goes into here to form it with this plus. Then we're going to go back to the normal state in a rather roundabout way. It's not really the mechanism, but it does resolve to the right place, which is here, back to a radical on this one. Dot, 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 plus dot. So now we've got our charge, our hole effectively has moved along 1 step, and we have to do the same thing again. Let's do it with single arrows this time to try to make it easier. So if we do a single arrow, then we have broken this bond, and I'm going to have to do a double arrow. Can we do it with single arrows? No, we can't. We can't do it with single arrows because we have to form that intermediate in between. So we have to go to here, because I need to get an electron from this ring into this ring, and to do that I have to form a double bond here. So I have to carry it across here. So I form the double bond, that forms this species plus, and obviously gets rid of the plus, and then we move it along one more. We can shuffle it along these nitrogens. There will be a nicer way of getting the charge, the radical back over. So I've got the plus over. There'll be a nicer way of getting the radical over. While we're here, however, we can see another thing about these, that this positive oxidized state is obviously not going to be very stable as it is, so it's going to need an anion, and typically we'll have a big anion to be relatively stable next to this polymer, so we will have some kind of let's have some soap. SO4. So a sulfate anion, and the anion will react, or will hang around near the positive charge, and obviously it has to move as the charge moves along the chain, but it might go slower, or it might be a different one that comes and associates with here. This one might just leave, so it doesn't have to move as slowly as the soap or whatever kinds of anions move in the liquid or outside. The charge doesn't have to move as slowly as that. It can move faster, and a different one can come closer, and this one can just move a little bit further away. What has this got to do with our subject? Well, this is now a material that will turn on and off in conductivity in response to a stimulus, which is now a redox stimulus. It's also a material which will swell and deswell in response to a redox stimulus. So this is the typical artificial muscle, in that when we oxidize this, so when we remove electrons from it, which we can do with electrochemistry, we can remove it by making both ends plus, so we make it attractive to electrons and pull out some of these electrons from the rings. Then some counter ions will move into it. We can only really do electrochemistry if we've got some kind of ionic liquid outside, so water containing salt, for example, and the counter ions move in, and those will be negatively charged. We can choose what they are by choosing what's in our solution. They will move in, and that typically brings some water with it, and that will make our material swell, and so it behaves as a kind of a muscle. It's a response, so it's a responsive material, a smart material. Another possibility that we can have, so we've got a chemical complexing which can form gels, break gels, attach to things, and it can also detect things. We've got redox reactions which can also form materials, change conductivity, attach things to each other. So we can generate a glue that reacts to a surface, that reacts to conditions using a redox reaction or some other kind of reaction. We can also generate some kind of motion in a smart material. A simple case that I have been considering, so let's start from a simple case because it's always a good place to start, is if we take a very thin cantilever, thin piece of tape for example, and we apply a layer of other material to it, which we will discuss in a moment, and then we put a drop of liquid on it. So now that we can discuss our materials, what I'm interested in here to generate an effect would be if this is something hydrophobic. Let's make this water to make it simple and non-toxic. Let's make this PDMS, which is a type of rubbery solid which we can make in a thin layer, and it's very soft and flexible, so we can change its shape. That's what I'm interested in. And it is also hydrophobic, it repels water, so if we put water on it, it would sit like that. It would wrap it up, depending on how thick this PDMS layer is and what happens afterwards, because there is an interaction between the water and the surface, but the amount of spreading is limited, so it would tend to wrap up around the drop and form some kind of shape depending on the size. If we have an intermediate material, which is, for example, sugar, let's put dextrose on there. Let's call it dextrose. So we apply some dextrose to it in a layer. It is difficult to get it into this shape, but let us start from this form, because the challenges of making it are not something that we are reaching just yet. Our water will tend to spread out on the dextrose, because dextrose attracts water. So let's do a step forward in time. Our water then is doing something like this. That's what it would do if the PDMS didn't wrap up. So first of all, we're imagining this PDMS layer is infinitely stiff. At this point, at some point, the dextrose will dissolve into the water. So then our drop will remember, or will notice that underneath there's some PDMS, and will return. So let's take that off to a new state where most likely there's a drop in the middle, and there are little drops here. This bit's going to be wet, and this bit is also going to be wet. So we have a drop in the middle. If we now do the same thing, but we allow this PDMS to bend, so we make it thinner, or we don't attach it to something infinitely stiff like a piece of glass, which is effectively infinitely stiff compared to water surface tension, which is the force acting here, then we will end up with a different situation in the middle. So when it spreads, instead of spreading, oops, I'm going to have to rub this out and do it in a different way. So we can see the starting condition and the finishing condition are the same. We've got water, a water drop at the beginning, we've got our layer, and we've got our PDMS and rubber at the bottom, and here we've got our water drop, we've got our layer, and we've removed our intermediate layer, and we've got some kind of blob at each end. But the intermediate step is the PDMS wrapping around the drop, and it depends, because if they touch each other then they'll probably get permanently attached. So it depends whether these two ends attach to each other or not, whether this becomes permanently attached or not. So whether we go to a state where this is attached to here, then we would have to peel it apart, or this stage, depending on what happens. We can modify this in various ways, so we can change the surface tension of the liquid, and we can change what is on here. So the more extreme example that I would imagine, and that I actually wanted to do, would be is if you took this to be mercury, and this was a layer of gold, because for practical reasons it's relatively easy to cover a piece of PDMS with gold, and then you would get it to wrap up and let go very strongly, because the surface tension of mercury is very high, but it also doesn't stick very well to other things. It, in fact, sticks incredibly badly to other things. We don't know whether this would happen. It might get stuck in some test versions, which I didn't use a coating. It tended to get stuck. It wrapped up and got stuck. But it is a possibility. So you can have a thing that changes from one form to another with a stimulus getting wet, and then it goes back again. It's all due to surface tension. Some groups, so some research groups, use a similar method, so wetting and drying, to form boxes and shapes, which are caused by the drying of a liquid drop typically. So as the drop dries, it evaporates. Obviously we wouldn't do that with mercury. It evaporates, and that changes the size, and eventually it leaves. And if it manages to get two sides to attach, then usually they stay. And if we can get the drop out without it all collapsing, without it crushing the whole structure, then we end up with a hollow structure. That's obviously not trivial, because we would have to modify the thickness or the stiffness of this material in different places to make it not quite shut, and we don't want it to shut, and make it stick where we want it to stick. But it is a thing that people investigate. How else could we do this, or how else could we generate motion? So we've already had the redox reactions generating motion by creating swelling. We can change surface tension, which causes motion. So if we imagine a surface of a liquid, let's call this water. We've got some water, and we apply something on the top, and it has different surface tension at each end. We can generate something. We'll put some soap at the back. We can generate a soap boat, where the surface tension of the water pulls in this direction, and the surface tension of the soapy water pulls not so strongly in the other direction, and we generate motion. That can only happen at an interface. But we can also do what other groups have done and generate motion in other ways. So a typical low-tech version would be if we take a bead and we have a piece of catalyst on one side, make it look a bit like an eyeball. If we do that, then we have to generate some kind of reaction mixture. So if we have something like peroxide, H2O2, it's a very common one used for this, and it is reacting to form H2O plus O2. Obviously we need two of those, and we get two of these to get O2. This catalyst is platinum, I think, typically. I think others work, but platinum is pretty good for this. And manganese also works. We could use that instead. Manganese dioxide is very good. We can generate a piece on a surface, generate an uneven particle of some kind, and because this is generating some kind of gas and it's also generating heat and some kind of energy, our particle will tend to move mostly away from it. Partly from the same reason that the interfacial tension here is lower, because it's warmer, and partly because we're generating products over this side, it will tend to move away in this direction. And a number of these have been made where the particles then move around in an interesting way. So the last thing that I'm going to do to put into this box of possible smart materials is self-healing. Self-healing is obviously in fantasy ideal. The robot in Terminator, whichever one it was, 2 probably, and a whole lot of other things, some magic materials in all kinds of science fiction series or even fantasies are usually self-healing in some way. And that's obviously scary to us because we see materials as fatiguing, getting worse, and then you have to do a difficult and involved process to get back to where you were at the start. If we have a material that can self-heal, it's way better because it behaves we can return to the original state, so we can break it and come back. We can absorb more energy effectively, and we are more resistant to change. There are 2 possibilities here. The normal, natural possibility is having a large number of weak bonds that can reform. So typically, if we have a polymer, for example, we have a carbon chain, and this is held together by connections between carbon atoms. If we have a metal, we have metallic bonds between metal atoms. If we break these, or even move them around, it is difficult, though not always the case. There are a few special cases. It is difficult to reform. So if we break our chain physically, then it is not going to go back to where it was. If we move the chains around, then very often we can get it to go back to where it was. So if we take a polymer, for example, a normal conventional polymer, and we stretch it and plastically deform it, which means it's broken. So we stretch it out of shape. If we warm it up very often, but not always, it can return to its original shape because the polymer chains have slipped over each other. Have slipped over each other, but their normal shape is wrapped up in coils and linked with each other in a loose kind of fashion, and they've drawn out, so they've become straightened. When we warm it up, they go certainly to a certain extent back. It's known as plastic memory. It works with acrylic quite well. So there is a sort of type of art where you take a warm stamp and you stamp your name into a piece of acrylic so that it's pushed into the surface. You then sand off the top surface, polish it back up to nice and clear, and then you warm it back up and your name pops out of the surface so it looks like you've made it specially. It's not a massive effect because there's a limit to how far these can move without forgetting effectively where they came from. But if we take a molecule and it's connected, let me try that in a different way. If we take DNA, for example, we can see that the DNA is held together, two strands of DNA is held together with hydrogen bonding, which is a very weak type of bonding. It's stronger than other types of interaction, of long-distance interaction, but it's not a proper bond. So there is a hydrogen bond between water molecules when they come up close to each other, but it still behaves like a liquid. At room temperature, it just lets go and goes and finds another water molecule. In DNA, it's very much the same. The two strands are held together with hydrogen bonds, and so if we apply a force to it, it will unzip, but as soon as we let go, it zips back together again. This is the principle behind pressure-sensitive adhesives. So if we look at a Post-it, for example, which I can't find right now, or duct tape. Americans call it duct tape because, well, I think that's a company name. It's duct tape for sticking ducts together. You can stick it on and you can peel it off, and if you have a good one, you can stick it onto something else. The adhesive doesn't stay on the other surface. It's not a very strong adhesive, in fact a very rubbish adhesive, but the combination of a large area and the bonding letting go slowly along means that we have to put in a lot of energy to peel it off, and we can push it straight back on again. If we want to use this for a self-healing material, we would have a material with lots of bonds in it that are weak, so not proper bonds, and then if we break the material, it can attach back together again. It does mean that the material will not be super strong because it's not held together by real bonds. DNA is not a structural material, but it will behave in a self-healing manner. We will have to weigh those two against each other because a normal conventional metal, for example, is way stronger. But we can, for certain applications, generate a material that if you break it, it goes back together. The ultimate version will be an insulator that I found. So instead of pouring a polymer into your electronics and have it insulating it, it is better under certain circumstances to not do that, to use a liquid instead. If we use a liquid, the advantage is if we have a bad event, if we have a high voltage event where one side is positive and the other side is negative, and we have a spark jump across through our liquid, it will form a trail of more conducting material, depending on what it is. If it's a polymer, so if it's some kind of hydrocarbon, it will be a trail of graphite, and that's obviously bad, but if we turn our power supply off, those particles will move away and it will be non-conducting again. And as long as we stay away from the bottom of the pot where it's going to fall to, then our non-conductivity will recover. There are types of silicone, which is like bathroom sealant, which are like that, but never set, and they never set deliberately because they can recover from mechanical and electrical damage. If we take the coatings on the ceramic insulators on high power lines, They are similar in that they contain small bits of monomer, of short, no, not really monomer, or ligamer of short chain silicone. And when a discharge happens, which happens pretty much every time it rains, the molecules move around slowly and it becomes hydrophobic again. When it's hydrophobic again, it doesn't have a layer of water on it, when it means it doesn't conduct anymore. These are, in most cases, so in a more modern case, there would be some kind of gel that then reforms or then sticks back together if you cut it. In the other direction, we could take a much stronger material, so we could take something that's maybe concrete. And the problem with concrete is if we try to break it, so we apply a force or we just age it in some way, cracks will form. So if we form a crack through it, that will seriously affect its strength. Obviously only if we load it in such a way that opens the crack, because concrete is very good in compression. It's not very good in tension, and that's particularly because of these cracks that tend to form. If we want to fix that, we could put some little hollow spheres inside our concrete, and they would contain maybe the two components of a two-component epoxy, which leaks out and glues the crack back together. It's a self-healing smart material. It is limited, so these smart materials that are self-healing can heal themselves every time they get broken, to a certain extent. If they get dirty, then they can't, but if we keep them clean, then they can heal back every time they get broken. And these self-healing materials have really one go. If we break the particles or the epoxy, whatever capsules, in one place, then it will reseal itself, but it won't do it forever. Self-healing materials are very interesting and useful, but obviously they aren't used very much. We don't see them in common use, and that's because they're expensive and they are hard to assess. If we put this into a road, for example, into a bridge, how can we tell whether it's cracked and resealed itself or not if the crack isn't as strong as it was before? And that's kind of the point. If it isn't as strong as it was before, then why do it? If we take this material, it's difficult to find an application for it because it's softer and not as cheap as a conventional material. So there are limits, but self-healing is an interesting topic as well. I will leave the smart materials there. There are also others, of course, but it would be a bit too much to keep going for too long. So let's stop there, see what you think, and then we will investigate it further.